So let's crack on with a couple of examples. The examples are slightly tweaked from the textbook, but I've given page references so you can see where they've come from. So example 1 here says 2 dice are rolled and the following events are defined. Event A is that the first roll shows a 4, and event B is that the second die roll shows a 4, and C is the sum of numbers. Got a bit of an erase there in the middle, sorry. The sum of numbers is at least 10 from the 2 die rolls. And the 2 questions are as follows: are A and B independent events, and are A and C independent events? Now, looking at part A there, you'd have to say that, logically speaking, A and B are independent because the roll of the first die would not affect the second die and vice versa. So there's a sense there that they're independent events if you think about the physical context. But we can use our calculations to confirm what we think is true. And the thing I find about probability is that sometimes common sense doesn't equate to what's the case because of some sort of underlying sort of principles. So confirming by calculations is often a good thing for people like me, at least, who get a little bit grey with probability sometimes. But it's not too hard anyway. So this is how you would go about it. This is a standard way of proving something is independent or not. We start off by looking at the probability of A intersect B. And we can see that if you imagine the sample space, we should know by now, that if you roll 2 dice, the sample space, assuming 6-sided, it would be 36 different outcomes, everything from 1, 1 to 6, 6. So 6 times 6 is 36. And A intersect B would mean the event that the first die is a 4 and the second die is a 4. There's only one way of getting a 4 and a 4. So that would be 1 in 36. Okay. The probability of A multiplied by B is considering them separately. The probability of A is that the first die shows a 4. Well, there's one way of getting a 4, and there are 6 sides on the dice, or 6 faces, so it's a 1 in 6. The probability of B is exactly the same, getting a 4, but on the second die. So that would also be 1 on 6. And if I multiply tops and bottoms together, I get 1 on 36. And if you want to be really fancy, you can say which equals probability of A intersect B. Okay, therefore, events are independent. Done. Now, I have seen some interesting settings out of people trying to prove independence and so on. They tend to sort of mishmash things around, and it's not great. So I really do recommend that you follow my setting out here. I think it's straightforward. You can not do this bottom line if you really don't want to, and that extra 3 seconds and 0.02 milliliters of ink is just too much for you to bear. Then you could probably stop without that line. But step 1, show what probability of A intersect B is, and step 2, show what probability of A times probability of B is. And if they are the same, then you can conclude they're independent. And if they are not the same, you can conclude that they are not independent, otherwise known as dependent. Okay, let's have a look at the second one. Now, I reckon personally that the second one is more tricky to see without calculations. Are they independent or are they dependent on each other? It's a sum of numbers at least 10 for event C. So would that depend on whether the first one is a 4 or not? Intuitively, I'd probably almost say they must be dependent, mustn't they? Because you'd need for one of them to be a 4. Not always, but sometimes. So let's spell it out. Maybe you could just, again, pause the video and think without doing the calculations. Do I think they'd be independent? Do I think they'd be dependent? And let's go from there. But you'll see the process is the same. So pause if you want to. So we're going to look at the probability of A intersect B to start with. And the probability of A intersect B, well, we need to know the sample space. And in part A, I just did the sample space in my head. This is a bit more complicated, so I'm going to spell out the sample space. But watch how I do it. I'm just going to do almost like a scratch pad over here to the side. 1, 2, 3, 4, 5, 6. I'm doing it as a lattice diagram, a table, because I think that would be the fastest way to do it. I'm not going to fill out everything though. I'm only interested in sum of numbers at least 10. So I'm going to just focus on that. And I know that 4 plus 6 is going to be the smallest sum to 10. So that's 4 plus 6 here is 10. Then I'm going to have a 5 plus 5 equaling 10. I'm going to have a 5 plus 6 equaling 11. 6 plus 4 equals 10. 6 plus 5 is 11. 6 plus 6 is 12. So there's my matching event. I know there are 36. Now I've got a count of the matching events here. All of these are event C, sum of numbers at least 10. But the probability of A, I should just fix that up. The probability of A intersects C is that the first row shows a 4 and it's a sum of at least 10. So in terms of out of those outcomes, actually which one matches both of them, it's only this one, assuming this is the first die row and this is the second one. Only that one matches, 4 and 6. This one doesn't match because this is on the second die roll. So only one matches. So the probability of A intersect B is 1. Oops, change colors. Is 1 on 36. 36 possible outcomes, only one of them matches. Okay, now we need to do probability of A multiplied by the probability of C, and that's a little bit easier to do. The code word for this video is bow ties are cool. Now, instead of telling me in class, I want you to email me the answer. So the first email I get, which has bow ties are cool in the subject or in the message body, you're going to get the chocolate prize, or if you don't like chocolate, something else. Where was I? Probability of A times the probability of C. So probability of A, we worked it out in part A, it's 1 on 6. The probability of C, we can see, is here. C is 1, 2, 3, oops, didn't mean to draw on it. 1, 2, 3, 4, 5, 6. There are 6 ways of getting a sum to 10. So it's 1 on 6 multiplied by 6 on 36. Okay? Or that's also 1 on 6, isn't it? 6 on 36, but it doesn't matter. I just put it down like this. The 6's will cancel out, cross-cancelling. And so I've got 1 times 1 on the top, which is 1, and 1 times 6 on the bottom, which is 1 on 6 again. So, sorry, 1 on 36, beg your pardon. That was a bit of a bad moment for me to get wrong. 1 times 36 is, of course, 36. So again, we have the probability of A multiplied by the probability of C working out to be the probability of A intersects C. So we can conclude, therefore, the events are independent. And this is one of those examples where I kind of feel at first glance the events feel like they should be dependent because there's something about the rolling a 4 that you would think would be part of the getting a sum of at least 10. So it feels like they should be dependent on each other, but our calculations show that they're not. And if I wanted to make the video much longer, I could probably then go back and think about, well, why are they independent? How does that work out? Why conceptually are they independent? Often with probability, I'm going to be straightforward, honest. I trust the calculations. I can't think of why they're independent, but I acknowledge that they are. But a better person than me would probably stop and think very carefully about why they would be considered to be independent from each other. But not me. Okay, I'll stop this video here in example 1. In the third and last video for independent probability, I'll go through one more example and then we'll call it quits.